All right, so chapter 11 focuses on the concept of ideal solutions. So before we get into talking about ideal solutions, I first want to take some time to kind of recap where we've been and then give you an idea of where we're going. Why are ideal solutions important and how are we going to utilize them in the next chapter, in chapter 12. Okay, and so what I want to start with is just talking about our definition of fugacity, first in the concept of pure solutions, and then we'll look at the case of mixtures. Okay, and so if we think back to our definition of fugacity, okay, starting with pure component systems. Okay, so I believe this was back in chapter 7. What we had was for an isothermal process. Okay, so I'm going to write isothermal here because this is key to remember. All right, our definition is only valid for an isothermal process. That the change in my molar Gibbs free energy from some state at T and P relative to some state at T, I'm going to write my pressure is P naught, right? Because I'm looking at an isothermal process. So I have the change in molar Gibbs free energy between two states at the same temperature, but they need not be at the same pressure, okay, is equal to RT times the log ratio of fugacity. So this would be the fugacity at T and P relative to the fugacity at the same temperature, but pressure P naught. Okay, and what I'm going to do here, just for completeness to kind of emphasize this point, I'm going to put a superscript naught on top of G and F naught, right? Because oftentimes we can just think of these as a standard state or a reference state that we're computing our molar Gibbs free energy or fugacity with respect to. So what's important here is that this is for an isothermal process. Again, so this is the difference in my molar Gibbs free energy between two states at the same temperature, but they need not be at the same pressure. Log ratio of fugacity, okay. This F corresponds to the same state as this G. F naught corresponds to the same state as G naught. So once you choose a standard state, right, for G naught, the state of F naught is fixed, right? They're one and the same. Okay. All right. So this is valid only for an isothermal process, but we're free to choose that standard state however we want. Okay, and so one thing we did is if we take our reference state to be an ideal gas, okay, then I get G at T and P, okay, and not only an ideal gas at the same conditions, okay, so you can think of it as a hypothetical ideal gas state at T and P is equal to RT log F over F ideal gas at T and P. Okay. Now, let's take an aside here for a moment. Okay, so remember the origin of this equation was that for an isothermal process for an ideal gas, a difference in molar Gibbs free energy was equal to RT log ratio of pressures. Okay, and so Lewis's idea then was to generalize this for real fluids. Okay, and so to make that generalization complete, it had to be that in the ideal gas limit, okay, so the ideal gas limit, or for an ideal gas, okay, the fugacity of my ideal gas, okay, we can even say at T and P, is just equal to the corresponding pressure, right? So if the origin of this is, for the case of an ideal gas, a difference in molar Gibbs free energies is RT log ratio pressures, right? Here we are just generalizing it, okay? We're generalizing that expression. And so the expressions must be consistent in the ideal gas limit. So it must be that the fugacity of my ideal gas is just equal to P, right? All right. And so, what becomes of this then is we introduce another concept or another variable called the fugacity coefficient. So the idea is I can write my fugacity as being equal to my fugacity coefficient times my pressure, right? Or I could equivalently think of this as fugacity coefficient times the fugacity of an ideal gas. Okay, so that for an ideal gas, okay, for an ideal gas then it must be that phi is equal to 1. Okay, so phi then serves as essentially a correctional term. All right, it's going to account for deviations from this ideal gas behavior. Okay, so all this discussion might seem a little odd, but we're going to try and recast these expressions in a way to give you an idea of what they mean. Okay, and so even just looking at this, then, as we introduce this concept of fugacity, it's already looking as a correctional term. All right, so now I've taken a side back here. Okay, so if I look at this expression, where I've defined my standard state as being an ideal gas at the same conditions. Okay, so connecting back up here. On the left-hand side, this would correspond to the residual Gibbs free energy at T and P. Which again is equal to molar Gibbs free energy at T and P minus the molar Gibbs free energy of a corresponding ideal gas at a given temperature and pressure. Okay, and so in the same light, right, this is our definition of the concept of residual properties. So if I were to rearrange this expression, my molar Gibbs free energy of interest then is equal to the residual Gibbs free energy at the same temperature and pressure plus the molar Gibbs free energy of an ideal gas at the same temperature and pressure. Right? So you can almost picture a residual property as being the same sort of correctional term, right? This correctional term accounts for deviations from my ideal gas behavior, my ideal gas limit. So that I can take G and write it as ideal gas term plus correctional term. Okay, cool. And so, ideal gas, right? Typically I can calculate ideal gas properties, fairly readily. We have the ideal gas equation of state, right? Those state, this system is well defined. And then I use our cubic equations of state to calculate our residual term, our correctional term. Okay. So, linking back up to this equation, right? So we have G of R, okay, which again, I'm just going to write as G minus G ideal gas, okay, is equal to RT log F over Fig, okay, which is equivalent to RT log phi, right? So this is just fugacity coefficient, okay? All right, so our next link here is RT log phi, all right? RT times the log of my fugacity coefficient is equivalent to my residual Gibbs free energy, where we just said our residual Gibbs free energy is essentially our correctional term, which accounts for deviations of my molar Gibbs free energy from ideal gas behavior. Okay, cool. So RT log phi, what's it correspond to? Well, it corresponds to my molar residual Gibbs free energy, right, which is going to account for the deviations of my molar Gibbs free energy from ideal gas behavior. Okay, taking it further, right, an ideal gas is a system in which molecules don't interact and don't take up space. So the residual Gibbs free energy is going to be the contribution due to the fact that molecules interact and take up space. All right, so far so good, right? So, and so all we're trying to do is keep recasting these things as correctional terms, right? And so, the idea is we define some idealized state, okay? So if I'm trying to calculate the molar Gibbs free energy of a vapor phase, right? You could think as a first order estimate, you could assume that that system could be treated as an ideal gas. And then we just use our equation of state to calculate our correction term. All right, cool. So GR is equivalent to RT log phi. Okay, so the next thing I want to do is, the key important relationship that we want to look at in just our definition of fugacity is G. Okay, let me see if I get my pen on here. Well, let me get my cursor. G, okay, G is always related to log F, right? G is related to log F. G is related to log F, okay? So while up here we said F is equal to phi times P or phi times F ideal gas, okay? We could equivalently write this in log form, okay? So now log F is equal to log phi times F ideal gas. And so via my log rules, this is log phi plus log F ideal gas. Okay, so again, right, what's important is we could take log F, okay, the log of my fugacity of my system of interest is equal to that of an idealized state, right, an ideal gas plus correctional term. Okay, so in the limit that I approach that idealized limit, okay, This term is just 0, right? Phi of 1, so log of 1 would be 0. My correctional term goes to 0. But as I deviate from that idealized state, right, my correctional term becomes more and more important. But as a first order approximation, I could just say, assume that my system can be modeled as an ideal gas. This term I can readily calculate. It's just P. And then if I need to, I can account for deviations from that idealized limit via my cubic equation of state, right, by calculating log phi. Okay, but the main concept is log f I write as being correctional term plus fugacity of an idealized state. Okay, I write my log fugacity as being correctional term plus fugacity of an idealized state. I use log f, okay, because it's log f that's related to g. Okay, this is in the same notion that up here I could take g, my molar Gibbs free energy of my system of interest, is equal to my correctional term, residual Gibbs free energy, plus g of an ideal gas. Okay, and in fact, right, these are in theory two equivalent expressions. The difference here is that g is this abstract quantity, f is something that has a little more physical basis to it. Okay. Cool. Okay, so far so good? All right. So log fugacity, correctional term plus fugacity of an idealized state, which here, so far, we've taken it to be an ideal gas. Now, if we were to move on to the case of mixtures, right, how do things change for mixtures? Okay, well, how things change for mixtures is if you look back to our definition of fugacity up here, it's just a matter of replacing G with our molar Gibbs free energy, and our molar Gibbs free energy is equivalent to chemical potential. Okay, so this just becomes G bar. Okay, I'm going to write subscript I, because it'd be, say, for species I in a mixture, at a given temperature, pressure, let's say composition Xi, minus G bar I naught at, okay, so it still holds, okay, that this is only going to be true for an isothermal process, okay, so the isothermal process part still holds, but that's the only part that holds. So my standard state will be at the same T, but it need not be at the same pressure, and it need not be at the same composition. Okay, so I get G bar I minus G bar I naught is equal to RT log Fi at Tp and Xi relative to Fi naught at Tp and Xi naught. Okay, and this would be Tp naught. Okay, so I still get now difference in molar Gibbs free energies is equal to RT log ratio of fugacities. Okay, where my state of interest, so G bar I and Fi correspond to the same state. G bar I naught and Fi naught correspond to the same state. The other way we could write this is my partial molar Gibbs free energy is equivalent to chemical potential. So equivalently, I have mu I at Tp and Xi minus mu I naught at T P naught Xi naught is equal to RT log Fi at Tp and Xi relative to Fi naught at T P naught and Xi naught. Okay, cool. Now, the one thing that is going to differ is for an ideal gas. Okay, so in the case of an ideal gas, remember this, right, we're looking at a mixture. So this would be component I in a mixture. So for an ideal gas, the fugacity of component I in an ideal gas mixture, okay, and let's say at T, P, in composition Xi, okay, isn't going to be equal to just the fugacity of, an ideal gas. Well, it's going to be equal to, what am I saying? It is equal to the fugacity of component I in an ideal gas, okay? But it's not equal to just P, as we had before. Now it's going to be equal to the mole fraction times pressure, right? Essentially, it's equal to its partial pressure. And so the idea behind the partial pressure, again, would be in an ideal gas, molecules don't interact and they don't take up space. So let's just draw our little picture and then we'll erase it. So the idea is I have some volume in which I have some of these non-filled molecules, and I've got a couple filled molecules. Okay, so what would the total pressure exerted by this system? Well, so our ideal gas equation of state takes the form PV equals RT, okay, where that's my molar volume. The other way I could write it is, P times V total over N is equal to RT, okay? And so if I want to solve for P, the pressure that would be exerted, or the pressure of this system, would be equal to R, so nRT, let me multiply by N, nRT over V total, okay? The idea behind the partial pressure is if I could say magically erase, all molecules except of, say species I, then it'd be the pressure that species I would exert if it were the only species present in the system, right? So the total volume's the same, RT is the same, but now the only moles that are left are that of, species I. Okay, so the idea behind partial pressure is an ideal gas mixture. If I could magically erase the molecules of all other species in my system, it'd be the pressure exerted just by species I. So where things change a little bit is in the ideal gas limit, the fugacity of component I in that ideal gas mixture is now equal to partial pressure. Okay, so got to go on to the next page. If we take our standard state to be an ideal gas at the same conditions, okay, I can write this as mu I at Tp and Xi, okay, minus mu I ideal gas at Tp and Xi at the same conditions. Okay, I'm going to make a note here. When we were talking about ideal gases before, typically I used Yi here for mole fraction because I think of it as a vapor, but it doesn't matter, right? This just means mole fraction composition. I'm going to use Xi because when we talk about ideal solutions in this chapter, we'll use Xi's because we're typically dealing with liquids. Okay. All right, so if I take my standard state to be an ideal gas, this is RT log fugacity of component I at Tp and Xi relative to fugacity of component I in an ideal gas mixture at Tp and Xi. Bam. Okay, well, again, fugacity of component I in an ideal gas mixture is equal to Xi times P, okay, which is equal to partial pressure, okay. And we, have the same concept of fugacity coefficient, right? My fugacity of component I is equal to fugacity coefficient of component I times fugacity of component I in an ideal gas mixture, right? And again, sorry if I'm all over the place, but this is just me rambling as if we were in class, okay? If I apply my log rules, I'd have log Fi is log Phi plus log Fi ideal gas, right? So the fugacity coefficient still has the same, principle as being a correctional factor, right? For accounting for deviations from this idealized state. And I like it written out in logs, right? Because now log Fi, the log fugacity of interest, is the log fugacity of an idealized state plus correctional term. Okay. Cool. Okay, and this is, as I mumble, this is what I'm, trying to emphasize, right? Fugacity coefficient of component I, right? This is my correctional term. Okay, this is going to account for deviations from my idealized state, which is taken here to be an ideal gas. All right, so if I come back up to this expression now, that would allow me to take, well, this left-hand side is just the residual chemical potential of component I at Tp and Xi, and that's going to be equal to RT log Vi. Okay, so RT log Phi is just equal to my residual chemical potential. Okay, residual chemical potential is going to account for deviations of my chemical potential from idealized behavior, from the ideal gas limit. Because, right, mu I, right, is just mu I R plus mu I ideal gas. All right, so residual chemical potential is that correctional term, accounting for deviations from ideal gas behavior. Okay, all right. Hopefully I haven't lost you quite yet. All right, So the next thing I want to look at is just looking at this expression. Okay, oftentimes I call this expanding my fugacity, right? So if I was interested in the fugacity of component I, right, I could expand it out as being correctional term phi times fugacity of component I in that idealized state, an ideal gas, which in this case is phi times yi times p. Okay, so now I have this correctional factor, and then, and I've been using xi, correctional factor times xi times p, okay, where this is just fugacity of component I in an ideal gas mixture or partial pressure, okay, but it's going to take the form of correctional factor. Then the fugacity of my idealized state, right, corresponds to mole fraction times this pure component property that's readily available, okay, mole fraction times p, okay, so this gives me an expression which is explicit in composition. Okay, and that's highly desirable because if I think about designing a distillation column, all right, what I'm ultimately interested in is what's the composition of my distillate and my bottoms, right? What's the composition of these two streams in coexistence, right? And so the fact that we can now get an expression which is explicit in composition is incredibly beneficial. All right, but again, it's going to take the form of Fi is equal to correctional factor times fugacity of idealized state, where my fugacity of my idealized state takes this form of mole fraction times pure component property, in this case P. Okay, and again, if I play with log rules, right, I get log Fi is equal to log Fi plus log Fi of an ideal gas. Okay, so hopefully I haven't lost you, but I'm trying to drive home, right, is in terms of expanding our fugacity, getting this expression which is explicit in x, right? What we're doing is we're taking our fugacity, so log f, and we're writing it as the sum of a correctional term plus that of an idealized state. So essentially it takes the form of sort of a perturbation-based equation, right? So I'm writing my log fugacity of my state of interest as being some perturbation from some idealized state. Okay, and so long as I am close to that idealized state, then I expect my perturbation term to be relatively small. Okay, and I would expect then that I should be able to calculate this term rather accurately. Okay, so the goal is to choose an idealized state so that my correctional term remains small so that if I needed to make a first order approximation or first order guess in terms of what my fugacity is, I could readily calculate the fugacity of that idealized state. Okay, and I don't want to deviate too far away from that idealized state because I want my correctional term to be as small as possible, which will make it as easy on me as possible to calculate. And by calculate, I mean calculate accurately. Okay, so log fugacity is correctional term plus fugacity of an idealized state. Okay, we want to choose our idealized state so that my fugacity is as close to that idealized state as possible, so that as a first order approximation, I can readily calculate the fugacity as the fugacity of that idealized state. Or if I need to calculate my correctional term, I don't deviate too much from that idealized state so that my correctional term is relatively small, ensuring that I can calculate it accurately. Okay? Now, what we've done so far is we've adopted as our idealized state, okay, so remember, this is my idealized state, okay, and this is my correction, okay, or my perturbation, however you want to think of it, okay. So far we've adopted our idealized state as being that of an ideal gas, okay. Well, what is an ideal gas? Okay, remember, an ideal gas is a system in which molecules don't interact and they don't take up space. Okay? All fluids approach ideal gas behavior in the limit that P goes to 0 or V goes to infinity at constant temperature. So riding along an isotherm in the limit that P goes to 0 or V goes to infinity, all fluids approach ideal gas behavior. Notice that constant T, right, for an isothermal process. Okay? So if I were modeling methane gas, okay, gas being the keyword. So if I'm modeling methane gas, okay, well, an ideal gas would probably be a very good reference date, okay, because I'm dealing with the vapor phase, which I don't expect to deviate too much from. Okay, so I should say a methane gas well removed from my critical point. All right. Well, even as you get close to your critical point, the correctional term just increases. So what I'm trying to get to with an ideal or with the vapor phase is your molecules are typically further apart. Okay. So if I think about molar volume of a system at vapor liquid coexistence, I can identify the vapor phase as being the system with the greater molar volume, right? Because the molecules are further apart, right? Intermolecular interactions are much weaker as compared to a liquid phase. And so if I'm modeling vapor phases, adopting an ideal gas as your idealized state is generally an incredibly good approximation, right? But what about liquids? Okay, so an ideal gas is a system in which molecules don't interact. In a liquid, this would be a really bad idealized state. Why? Because in a liquid, we know that molecules interact very strongly. Okay, in fact, it's molecular attractions which cause liquid phases to even form, to exist. So if I'm trying to model a liquid phase, if I were to adopt an idealized state as an ideal gas, that would be a rather poor approximation, right? Why? Well, as a first order approximation, my liquid phase is not an ideal gas. And then if I were to try and rigorously calculate the fugacity of that state of interest, I'm going to be dealing with a very large correctional term. Okay? So I'm going to deal with a large correctional term, and so there's going to be some questions then in terms of my accuracy to be able to calculate said term. Okay? This is me putting terms loosely to try and drive home the idea. Okay? And so what's going to happen is, we're going to define a new idealized state. Okay, so rather than taking our idealized state to be an ideal gas, we're going to adopt an idealized state of, or as, an ideal solution. So while in an ideal gas, molecules don't interact and don't take up space, in an ideal solution, we're going to assume that molecules interact and that molecules take up space. Okay, what we're going to assume, right, that makes our solution ideal is that in that mixture, all of our molecules interact in exactly the same way. So if you have a mixture of, say, A molecules and B molecules, we're going to assume that an A molecule interacts with a B molecule just as an A interacts with an A and a B interacts with a B. Okay, so it's going to be a system in which molecular interactions are present and important, but the assumption is that all of our molecular level interactions are exactly the same. Okay. And so what we're going to do then is this will typically be used when we model liquid phases, is we're going to take our fugacity, okay, log Fi, okay, and we said we're going to write our log fugacity as correctional term plus idealized state, okay. And so what's going to happen, okay, is our correctional form, we're going to give a different Greek symbol, okay. So this is fugacity coefficient, which tells me correctional factor relative to ideal gas. Gamma I, my activity coefficient, is going to account for correctional factor relative to an ideal solution, plus log Fi ideal, the fugacity of component I in an ideal solution. Okay, so we're going to introduce this concept of ideal solution. Motivation being is that I still want to be able to write log Fi, the log of my fugacity of my state of interest, as correctional factor plus fugacity of my idealized state. Okay, so this is still my idealized state. This is still my correctional factor. Okay, but now we're redefining our idealized state so that it's more close or more representative of my actual state of interest. Okay, so that, as a first order approximation, I could take the fugacity of my liquid phase as being that of an ideal solution. Okay, so remember, an ideal solution now, molecules take up space, they interact, it's just they all interact in exactly the same way. And then I'll have my correctional term, which will account then for the fact that molecules don't interact in exactly the same way. Okay, but this is going to be much more manageable or reasonable to calculate accurately. Okay, so we're applying the same principle, but we're going to redefine our idealized state so our state of interest is closer to this idealized state as compared to before, if we stuck with using an ideal gas when modeling liquid phases are going to be pretty far away from that ideal gas behavior. Okay? And it just so happens, okay, remember we said, okay, up here, that, the fugacity of my idealized state is always essentially going to be mole fraction times, this pure component property, P. Well, the same thing's going to happen here, okay, and what's going to happen is that the fugacity of component I in an ideal solution is just going to be mole fraction xi, times, I shouldn't write it as this. I should write it as xi times fi pure. Okay, I went to write pi sat because when we use Rails law, it's xi times pi sat, but there's some assumptions that go into that we'll have to work out. Okay, but the fugacity of component I in an ideal solution is just equal to xi times fi pure. You know what? This would be fugacity of if it was a system of pure component I suppose. Okay, but fugacity of component I in an ideal solution is just going to be mole fraction times pure component property, which we can calculate. We've done that before. We've calculated fugacities of pure component systems. All right, so where we're getting at then in chapter 10 or chapter 11 is our focus is on this term. Okay, so we're going to look at the concept of ideal solutions. We're going to talk about calculating the fugacity of ideal solutions. Okay, we'll derive this expression. Okay, and our goal for doing this is that now in chapter 12, when we begin to model real liquids, okay, and we want to calculate our fugacity of a real liquid, okay, we're going to adopt as our idealized state the fugacity of an ideal solution. Okay, and then we'll introduce this new correctional term, which is called my activity coefficient. Okay, but it's the same principle, right? We're trying to calculate fugacity of component I is correction factor plus fugacity of an idealized state. When we're dealing with liquid phases, we're going to define our idealized state in a different way so that our system of interest here, a real liquid is a real liquid mixture is closer to that idealized state as compared to, say, if we were to adopt an ideal gas as our idealized state, right? So all we're doing is we're changing how we define our idealized state. Okay, so for liquids, we'll typically adopt an ideal solution. For vapor phases, we'll typically assume an ideal gas. And then when we adopt these different reference states, our correctional factor changes. Okay, and when we model vapor-liquid coexistence, common term that may come up is a gamma phi method, and all that means is you're using gamma, right, a correctional factor corresponding to ideal solution to model liquid. Phi, right, meaning you're modeling the vapor phase is taking that reference state to be an ideal gas. And I think that's all, right? Just one comment based on this to make this complete. Gamma I is just Fi over F ideal, right? So it's just like Phi is Fi over Fi ideal gas, right? It's one and the same. You can use logs and expand it. And then, we said, we can, expand our fugacity. So if I needed to calculate, Fi, if I were to adopt an ideal gas as my standard state, that would take the form as Phi, and then I could write it as Fi ideal gas, okay, or, say Xi times P, okay. I could just as well expand it as gamma I times Fi ideal, which is equal to Xi times Fi pure. Okay, so these two expressions are related to each other, right? These must be equivalent. These are equivalent expansions of Fi, right? And so you could cancel the Xi term if you were to equate these two terms, right? But there is a relationship between Phi and the fugacity of an ideal gas and gamma I and the fugacity of an ideal solution, right? So that is Phi times Fi ideal gas is gamma I times Fi ideal. Okay, and so all I'm trying to get at in this is that these two different expressions, these two different expansions are equivalent. All that differs is I'm defining my idealized state in a different way, and hence then my correctional factor in a different way. But they're just going to be different expressions to compute the same thing, fugacity of component I. They're going to have different utility depending on the system I'm trying to measure, right? I'm going to choose the convention so that I'm as close to my state of interest. My idealized state is as close to my system of interest as possible, okay? So takeaways from this, okay, is, okay, in general, we write our fugacity as being correctional factor times that of an idealized state, okay? So far, we've adopted an ideal gas as being our idealized state. In that case, our correctional term is our fugacity coefficient. This will be useful for modeling vapor phases, in which I don't expect my system to deviate too much from that ideal gas limit. Phi then, okay, we typically readily calculate it from cubic equations of state. Okay, RT log phi is equal to my partial molar residual Gibbs free energy, right, or my residual chemical potential. Okay. When we come to modeling liquid phases, adopting an ideal gas reference state as our standard state typically isn't as good, right, because we expect our liquid phase to be much more different as compared to that, ideal gas in which molecules don't interact and don't take up space. So we define a new idealized state, which is my ideal solution, and I write my fugacity, log fugacity, as correctional factor, where now I use gamma because I'm going to define my correctional factor in a different way, right? It's a different correctional factor for different idealized state, plus now my idealized state is an ideal solution, so this is log Fi ideal. Okay, and so if you want to calculate your fugacity, you could expand these things in the same way, right? They're related. It's just I'm defining an idealized solution or an idealized state in a different way. Okay, and just like RT log phi was equal to partial molar residual Gibbs free energy, I'll show that RT log gamma I is equal to my partial molar excess Gibbs free energy. So residuals, relative to an ideal gas, excess is going to be relative to an ideal solution. Okay, and so when we get to those in chapter 12, hopefully they come full circle, right? And so, just to give you an idea, these will be things way out in the future. Well, not in the way out in the future, next chapter. But RT log phi is equal to G bar I residual, which is GI minus GI ideal gas. Okay, RT log gamma I will be G bar I excess, my partial molar excess Gibbs free energy, which will be GI minus GI ideal solution. Okay, and so just as this was equal to my partial molar residual Gibbs free energy, which gives me deviations of my molar Gibbs free energy from ideal gas behavior, this is going to correspond to partial molar excess, which corresponds to deviations of my molar Gibbs free energy from that of an ideal solution. Okay, so conceptually they're one and the same. We're just introducing a new correctional factor defined with respect to new idealized state, so that when we go to calculate the fugacity of a state of interest, we can choose our idealized state so that we are as close to that idealized state as possible. Okay, so modeling liquids, we'll adopt an ideal solution. Modeling vapor phases, typically we'll adopt an ideal gas. Okay, cool. So you could adopt a fugacity coefficient to model your liquid phase and calculate coexistence using an equation of state, but a much more common convention is typically to model it as an ideal solution. Okay, or it is deviations from ideal solution when it comes to that liquid phase. All right, I'll cut myself off there, and the next screencast we'll start to look at, again, our focus in this chapter is ideal solutions, and then ultimately calculating the fugacity of an ideal solution.